Hello, today I'd like to talk about Monte Carlo Ray Tracing. So these are the today class objectives. I wish at the end of this lecture material, I wish you understand the basic structure of the Monte Carlo Ray Tracing. And then we'll talk about some of the detailed technique for the Monte Carlo Ray Tracing, which is nothing but path tracing. We'll talk about also the Russian roulette for to terminate the recursive Monte Carlo Ray Tracing. So you may recall that last time we talked about Monte Carlo integration, which is nothing but a sampling approach for the solving the very complex integral equation. Today we will actually apply this Monte Carlo integration to this ray tracing to solving the random equation. Let me recall this random equation. Suppose that we want to compute the reflected radiance from the point x. Let me use the mouse pointer. This point x in the direction of this big theta. Then to compute that radiance, we need to put the hemisphere here at the center of this x, and then we need to consider incoming radiance in the incoming direction of the put side to the point x, and then we need to consider the BRDF adjusted by the cosine theta. Then if we consider all the incoming radiance, then we can compute this reflected radiance. Then here, to solve this reflected radiance, we need to consider this incoming radiance, right? So if we visualize this incoming radiance into the rectangular shape, basically we actually put the hemisphere, right? And then we just transform that hemisphere, the region into rectangular shape. This is actually incoming radiance. You can see that at that point, we can see the light source, and here actually we don't have light source, but we can see this surface, this material, since there could be the reflected radiance again here, right? So the random equation to solving to compute the reflected radiance, we need to consider this incoming radiance. Before I talked about the reflected radiance, but now I talk about the overall radiance from the x to that direction, outgoing direction of theta. Then first, in terms of algorithm wise, we need to first check whether that the material x is actually the emitted. Does it emit something? So in other words, is it some sort of the light source? Then we need to consider the reflect radiance, right, by solving the random equation. So that random equation is complicated integration, so we can use the sampling approach, specifically this Monte Carlo approach. Then we generate random direction on the hemisphere using the big psi, using some sort of the PDF function. Let's say p of this psi. For the time being, you can just using some sort of the uniform sampling of the hemisphere. Then the reflect radiance shown the reflect radiance represented in the random equation. We can actually compute we can apply the Monte Carlo integration. Then this is our Monte Carlo estimator. So we take the n different samples and we sum them up. This one divided by p of the psi I, and then since there could be there are n different random number, we need to take the 1 of n. Then this is our this unbiased Monte Carlo estimator. Then the question is that here n is known, this is already given. We define this uniform sampling for p of psi I, and we know this BRDF at that position. Also, we know the cosine theta value. But one thing unknown term is this incoming radiance. Basically, to compute the outgoing radiance, we need to know we need to again compute the incoming radiance to the point x in the direction of psi I. The question is how can you compute this one? As you can see, there are recursive structure again, right? And this one actually, this x, and then we need to compute the radiance value from here in the direction of psi I value to the I, right? But we just assume this reciprocity of this radiance value. So we can just the radiance value from here to there is same to the radiance value from here to there. So that we can simply using the ray tracing in a backward way. So we just compute the ray tracing from the direction x to there. So then basically to compute this outgoing radiance, we need to compute we need to perform this ray tracing in a back we need to perform this process in a recursive way. So also as you can see, each additional bounds supports one more indirect illumination, right? So by considering the backward direction, we can consider one bound from here. We having the one interaction from the light source and material, and then we need to compute the reflect radiance. So as we have these more bounds, we can actually consider more indirect illumination, and then we can compute the additional bounds, and then basically we can get a better result for the global illumination. Then the question is that when we have to terminate this recursive process, and basically this is actually visualization of as we have the more bounds. As you can see, this initial bounds. So at the initial bounds, actually there's a light source. We can see that. Otherwise, we don't see any light value since we just here. But as we have the more bounds, we can get the more additional. We gather additional light source. As you can see, we can get a more better and better result considering this global illumination. Then you can observe that as we have the when we consider only the one bound, second bounds, you can get a lot of the additional light energy. But as we have more bounds, the delta from by having the additional bounds is actually becomes small. So contributions of further light source further bounds become less significant, right? So that actually we can consider some sort of max recursion. Say we can just consider only 10 recursion, right? And then we only allow the up to 10 recursion, right? We can do that. But actually, if we just ignore at the point once we reach the max recursion and then we just terminate it, then it means we just simply ignore all the additional light energy that comes from the additional bounds more than 10, right? Then estimator will be biased. So basically, Monte Carlo approach is unbiased, right? But if we adopt this kind of the deterministic approach, it will be it cannot be the random process. It is actually, it has some sort of the deterministic approach. It introduces some sort of the bias. So we need to rely upon some sampling approach. To terminate this infinite recursive process, we typically use this Russian roulette. So suppose that we wanted to compute this integration. So we need to integrate in the range of 0 to 1 of the for the function f of x. You can basically we can visualize this function as shown here. This is 0 to 1, and then the function f of x is this black curve. And then to solve this process, we can also use this simple trick. We substitute y. Basically, we define the y as y to be equal to the p of x, p and multiply x, and p is the some number in between 0 to 1. So you can see that p is 1. And then our idea is that we wanted to make the final function to be 0 in the range greater than p. So at that case, we don't get any value. So that actually, in other words, it can technically terminate this recursive process. Since we cancel the value to be 0 here, right after p, we need to compensate that value, right? So that actually for other range that less than p, we need to actually make this function bigger than the original function. So basically, you can see that we can actually transform this function into this blue function like this. So in other words, we actually substitute y to be the p multiplied x, and then this function actually reformulate like this. We integrate the 0 to p, and then we got in the range of this y value, and then we get this function. And then basically this is our Russian roulette estimator. Then if this x when you generate random number xi is bigger than p, then we got the 0 value. But the random number is less than p, then we got this value. So f of xi divided by the p actually. Yeah. So basically this is our final integration. then one can show that the Russian roulette estimator is unbiased. I'm not going to talk about the detail here, but I think that my book already showed that this unbiased. So if you're interested, you can look up you can refer to my book. And then intuitively, we can say that the variance of Russian roulette is bigger than the original one, right? Why? At the case we got the 0, but in this region we got much bigger value, right? So the value actually change more, so the variance becomes more the higher. But even though each variance are higher than the prior one, we can at the case once the random number turn out to be bigger than p, we can terminate the recursion process. So actually, this is we can adopt this process. So and then the 1 of p is the absorption rate, absorption probability alpha, and then as an amount of alpha, this recursion is terminated. And then the p-value is basically p-value is set to be equal to the reflectance of the material of the surface, right? Basically, in the range of p, we actually somehow reflect the energy, right? So that once we know the reflectance value of the material, we can define the p-value, and then accordingly we can also compute this alpha value. So in summary, so in the past, we were actually talking about the past ray tracing. We actually generate multiple primer rays through each pixel, and then once the primer hit at some material, then we also generate indirect rays or sample over the hemisphere, right? And then we keep doing this recursive process, but we terminate this recursion process by using the Russian roulette. This algorithm, so far, it's not a past ray tracing, but actually past ray tracing actually has a very minor change into this algorithm. So basically, this Monte Carlo ray tracing, which seems very simple. And basically, we can compute the radiance value only at the center pixel. But if we do that, actually, this will generate aliasing, also known as this jaggies. So basically, we typically, to address this aliasing, we generate multiple rays even at each pixel, right? So then we can just, in other words, we can just use the Monte Carlo approach. We can generate n different samples within this pixel, and then once we compute the radiance value for each ray, then we compute we evaluate the Monte Carlo approach, and then we just take the average, which is known as the simple box filter. I can talk about a lot of things why this averaging method is a box filter, but this basically I'm not going to talk about the details here, but basically this is the averaging method actually turn out to be the box filter shape in the frequency domain. So there could be the many different parameters. So far, I'm talking about the Monte Carlo ray tracing, also known as this stochastic ray tracing. We can have the number of the starting number of the primer ray per pixel, right? And then it depends on n in the Monte Carlo ray tracing. Also, there could be at each intersection point, we can generate another multiple random indirect rays, right? So there could be the number of the random rays for each surface point, which is actually intersected point with the primary ray. This is known as this branching factor. But past ray tracing simply use the one branching factor. In other words, so to compute this, let's say this is our the radiance outgoing radiance value that we want to compute. Then at that point we generate one indirect ray, and we just generate only one ray. And for this one, and then also we need to compute this. Also we need to compute the additional indirect ray, right? But we also consider only one ray, not a multiple ray. So as you can see, there are paths right from here to there, right? That's why by using the one branching factor, basically we since it generates one path, so that's why it has a name of path tracing. And then basically the Monte Carlo ray tracing is that for this one, let's say this is 1 pixel, right? And then for one primary ray, we compute this one pass, right? And then basically we can adopt this multiple Monte Carlo integration here, right? So we generate another random number within the pixel here, and then we generate the that pixel, and then we also to generate another primary ray. We generate another indirect ray, and keep doing that. We can generate this multiple samples within each pixel and take the average. That's actually the path ray tracing. So this is the result when we use the path tracing. This is the result, the rendering result when we use one sample per pixel. So in each pixel we just use one sample. So then in other words, we generate one primary ray in each pixel, and then we compute we compute the one path, right? So as you can see, since there are only one path in each pixel, you can see that it has a lot of noise. But when we are using the four samples per pixel, it gets better. And then we generate 16 SPP, we got a much better result. In this case, we use the regular pixel sampling. Also, we additionally used the light source sampling by considering this importance sampling, which I didn't talk about yet, but I will talk about this issue later on. But anyway, by using these two different sampling techniques, pixel sampling and light source sampling, you can get this kind of result. So in summary, we generate the primary rays through each pixel. Also, we shoot indirect rays over the hemisphere, but path ray tracing shoot only one indirect ray, and then we keep doing that, and then we generate paths, but we terminate this recursion process using the Russian roulette. We can use this path ray tracing, but it takes a lot of time. We need to generate a lot of rays and samples to generate a very clean image. So ideally, we want better quality with a small number of the ray samples. So there has been a lot of techniques. So one of very well-known techniques, quasi Monte Carlo technique. Basically, there's one difference over this path ray tracing. This quasi Monte Carlo technique is actually using this deterministic well-distributed samples. Looks like the random sample, but which is not a random sample. But actually, since this is not a random sample, it has a much more complicated theory. I'm not going to talk about this quasi Monte Carlo one, but its main idea is that somehow we want to achieve the better quality with a small number of samples. Also, we can use this adaptive sampling. So in some region, we might get a much better. In some region, we might get a lot of noise. Then we can generate more rays on their region, and then by doing that, we can get a better result, right? Better quality with a small number of the samples in overall. That's the adaptively we generate samples, so known as the adaptive sampling. And this is another example. This is actually uniform sampling result, 64 samples per pixel. But here, as you can see a lot of these aliasing. You can see there are a lot of noise here, right? But this is actually reference. In other words, the reference is that we generate the huge amount of the sample per pixel. So then we can use it as a reference. And then if we're using the adaptive sampling, maybe in overall we might use the 64 sample per pixel on average. But since we got the more noise here, we generate more rays, and then we use less rays on the this kind of clean regions. So that's why by using the same amount of the ray, we can get a better result, which is more similar to this reference result. So far, before I briefly talk about the importance sampling, but here I'd like to give the one concrete example of the importance sampling, specifically this light source sampling technique. So this is our random equation. Here actually to compute the radiance value, we need to consider the incoming radiance, right? But if we visualize incoming radiance like this, as you can see, we can get a lot of light energy from the light source, but we got the significantly lower energy on other regions, right? So then, basically, importance sampling. The main idea of importance sampling is that we wanted to generate rays on the region where we got a lot of much more energy, right? By generating random sample on the light source, we can reduce down we can catch the most of the light energy, and then we can reduce down the variance. That's the one of the concrete example of importance sampling, also known as this light source sampling. So somehow given the incoming radiance, we actually decouple them into two regions: radiance from the light source, and then another radiance from other sources, right? So we cannot if we can only generate only 10 rays. Obviously, if we generate about 8 rays on this region, since we can get a much better we can get we can capture the much more the light source, right? And then we generate only 2 rays on this region, since even though we generate more rays on this region, we cannot get a lot of energy. So that's the one of the idea of the light source importance sampling. So again, we somehow decouple this actually the reflected energy. We somehow decouple them into the direct coming from the light source, another indirect one, and then we actually have the two different sampling technique for the direct, indirect with the separate Monte Carlo integration. We can just using the different Monte Carlo estimate for this region and that region, right? And then if we do this is two results with and without considering direct illumination. Direct illumination is that we use the important sampling for the light source. If we just random sample by without considering light source, even though we are generating a lot of ray, most of cases actually end up with non-emitted surface, so the image looks very dark. But if we consider the light source, when you generate 16 samples per pixel, we can capture a lot of energy here, right? Even though it's noise, actually you can see that we can get a much brighter result by considering light source. That's the main benefit of the important sampling, and especially light source important sampling. Another result: 1 sample per pixel for 16, 256 samples by considering this the direct and indirect illumination. Okay, so far I talked about the basic structure of Monte Carlo ray tracing. I talked about the Russian roulette for terminating the recursive process of solving the random equation, and I talked about the passive ray tracing, and then also I briefly touched on the important sampling, especially for sampling light source. And that's it. And then next time I will actually continue on I will talk about some of the acceleration technique for the Monte Carlo ray tracing. Thank you. Oh, okay. I will talk about acceleration technique for the global illumination technique next time. Thank you. Bye.